Okay, let's try this for the third time. I'm just gonna run through what I had already done. I deleted the second video I tried with sound, but it also did not have sound. So what we have here is a hammer or a big mass that is hanging from like a construction crane or something like that, and it's trying to drive what's called a pile into the ground. And each time the hammer drops, it's going to drop the whole system, hammer and the pile, down further into the earth. And so they give us that delta y is equal to 0.5 meters to start with. It's released from rest. And they want to know what the impulse is that's applied to the system. We can look at the impulse applied by the hammer or the impulse applied by the pile to the hammer, as long as we look at the correct momentums for each, we can get the same solution. But first we should start by finding out how fast the hammer is going before it hits the pile. If it's released from rest, I'm going to conserve energy first. We can say T1 plus V1 is equal to T2 plus V2. It has no kinetic energy, so I crossed it out. It was released from rest. It does have some potential energy, some MGH. They told us it was 0.5 meters above the ground. It is all going to turn into kinetic energy, RT2, right before it hits the pile. And it will then have no potential because I'm going to call the top of the pile y is equal to 0. If we throw in our MGH term and our 1/2 mv squared term, the masses cancel, and we get the velocity is equal to the square root of 2 times gravity, or the coefficient of gravity on Earth's surface, times the height that it is falling from. And we get a positive 3.132. I gave it a negative sign because we're going down. Okay, the next thing we should do is conserve momentum. We need to know how fast both of these are moving after the collision. So we are going to assume that the hammer and the pile move off as one, as the problem states in the text. So I have, if I'm looking right here, the mass of the hammer times the velocity of the hammer. That's the initial momentum. The mass of the pile times the velocity of the pile. Well, the velocity of the pile is 0, and they're going to move off together with a combined mass at some combined final velocity. So that the speed that we found earlier, 3.132, we can use that as the velocity of the hammer, and that's going to give us the fact that both of them are going to move off down at 0.85 meters per second. Okay, we have the velocity of the system now after the collision. Next we can find the impulse like they asked. So I'm going to go ahead and say impulse momentum theory should be applied. Let's say the impulse on, you can do this on the hammer or the pile. I'm going to choose to do it on the hammer. The impulse on the hammer plus, the momentum of the hammer plus the impulses applied is equal to its final momentum. And so what kind of impulse are we looking at? Well, we're looking at the impulse caused by the reaction forces. As one mass drops and hits the other, it's going to provide a reaction force from 1 to 2 or from 2 to 1, and those are equal. So that's why we can look at the impulses applied by either, we can call the reaction 1 or reaction 2. So the pile is not moving initially. we have the mass of the hammer, we know its initial velocity, we know how fast the hammer is moving after the collision. Therefore, we can figure out what kind of impulse had to take place, because if you remember, an impulse, when we derived it, was equal to a change in momentum. So if we know the momentum before and we know the momentum after, we can find out what that impulse is, giving us 383 Newton seconds.